Started, and we have this counter count multi-stage extraction. We already started this one this morning, and we'll inshallah continue. I don't know if you have any questions so far regarding the one-stage extraction. If no more questions, no more questions. Okay, let's then move on and start the what we did this morning lecture. Okay, we have this counter count multi-stage extractions. Basically, you're going to have the feed going from one side of the multi-stage kind of a column or stereo. You're going to have the solvent going from the other side. It's very similar to the counter count heat transfer equipments, probably you already know. Now, the extract, which is the product that you wanted to produce with certain specification regarding the composition of the solute, is going to go from the other side, and the raffinate, which is the residual or the waste of the remaining feed with certain composition. So now I have stage one that is going to represent the feed entrance. The stage number N, which will be maybe 2, 3, 4, whatever number, will represent or will take the solvent, inlet solvent. Okay. Now we usually have this composition of the solvent, the solute in this. The solvent is usually 0, but just to make the equations more general, we use the symbol YS to represent the composition of the solute in the solvent. Now, for each stage, I have 4 streams. Now, as you can see, for example, in stage number 1, I have the feed goes into that feed, to that stage, and I have the outlet, which is going to be named R1 and XR1. Okay, so it means you have the composition of the solute in the raffinate effluent from stage number 1, and we have the extract going to stage number 1. It's called E2 now. Why we call it E2? Because it's coming from stage 2, the second stage, and therefore we're going to have the composition. We can call it Y if you want, or we can call it X. So let's continue with naming it Y2. So now you see here the Y1 and X1 or XR1 are at equilibrium. So these two are, let's write them this, at equilibrium. So you have equilibrium relationship that you must satisfy, or at least around the system, which is the first stage you should satisfy, plus the material balance equation that you must satisfy, since it is a steady state process. So for each stage, you're going to have these equations we wrote previously. So we have F plus S, which is the total flow of the feed goes into the process of n number of stages, plus the solvent, which is going to the process itself. So F plus S must equal the outlet, E1 plus the Rn. Now Rn represents the raffinate effluent or the raffinate or residual leaving the stage number N. Okay, and your job is to specify or determine the number of stages that is required to achieve certain recovery of the solute from the feed. So you want to calculate, let's say, for example, number of stages, similar to the procedure we followed in the distillation procedure, but now we have a little bit different way of representing the equilibrium data here. We have ternary systems, so we have to use trigonal. Okay, so we have the overall balance F plus S is going to equal E1 plus Rn, and this summation is going to be constant forever and is equal to M. It's represented by M, which is exactly the same as we did for one stage process. Now, if you write the component balance, and the component we're referring to the solute here usually, we use the symbol A for the solute. But usually if I say XF now, by default, XF represents the composition of the solute in the feed, and YS represents the composition of the solute in the solvent stream, which is going to be used to achieve this kind of recovery process. Now, so that means the XM, which is the composition of the solute in the total mixture, represented by XM here, is going to be F multiplied by XF plus S, which is the flow rate of the solvent, multiplied by the composition of the solute in the solvent, divided by the total of the feed and the solvent. Now, as I said before, usually we have Y is equal to 0, because simply we usually use pure solvent. So, but you have to include it in the equation just to make it more general. Now, if we rearrange this equation and we write another equation for this, if we use this one and this one, I can have, for example, E1 here plus Rn is equal to M also, and is equal to F plus S. So it's basically the same equation. So if we rearrange this one, if we say Rn and we take S here with this one, so it's going to be Rn minus S is equal to F minus E1. So as you see here is the difference between the inlet and the outlet, as you see here, and the difference between the inlet and the outlet. So this one is the net inlet to the process, which is represented mathematically by F minus E1, and the net outlet from the process, from the overall process, is represented by Rn minus S. So this will represent the net outlet from the extraction process, from the outlet extraction. So please make sure you pay attention too much to this kind of terminologies. Then these are kind of it explains the behavior or the how you're going to be able to solve the problems in liquid extraction. And sometimes you will see these kind of words in the statement of the problem. So please make sure you understand each and every single word here to be able to understand the physical meanings of the problem of liquid extraction. So now this one, Rn minus S and F minus E1, they have the same number, by the way. And this one, since they have the same number, they are represented by what we call it delta, little delta R, which means the difference point. This different point is something that we want to use. Then it is not something just randomly generated, but because it's very useful when we're going to count the number of stages in liquid extraction. It's very similar to the OD, if you remember that OD and OW when we did Paschen-Savarite method in binary distillation. We had this OD and OW fixed points we use to draw the other mass balance line. So basically, if I ask you what you are doing in liquid extraction, you can tell me easily we are solving equilibrium equations plus material balance equations around each stage. And we try to use this, or we try to solve these equations using graphical approach. That's all what we are doing. But and the line represented by delta R is going to represent or is going to satisfy the material balance equation, and the line representing the tie line between the, for example, y1 and x1 and y2 and x2 and all these is going to be is going to satisfy the equilibrium line. We call it tie lines. Okay, so now basically what you have here, let me go with this one. Tamam, let's move on, and this one is already explained here. So basically, let me just go back to this diagram, and so usually this is what you have ready for you, regardless of the specification. This is your system, this is your carrier, and this is your solvent, C, and A is the solute. And as you see here, A and B are miscible all the time. So with any fraction of A and B, all the time your mixture between A and B will be homogeneous. So there is no any two faces going to be formed. But now, in order to bring that feed here, let's say, for example, you have 50 or 30% of your solute in the mixture here. So let's say this is your feed here. And let's assume you have pure solvent. So this is your pure solvent here. Okay. So what do you have to do? You're going to connect the point of the feed plus the point of the solvent. This is the first line you're going to draw. And this will represent XF and YS, even though it is 0 here, YS. And you're going to have another line that is going to be represented by the Y1 and XN, or the raffinate composition. So now let's assume this is your raffinate, and as you see here, we have to draw this point on exactly the line, equilibrium line, because this one leaving stage number N, and it is at equilibrium with, let's say, Yn. And Y1 is also should be drawn exactly on that line, on this line, because that Y1 is actually at equilibrium with X1 or XR1. Let's call it XR1. So now that line should be somehow like this one. So this is going to be E1 and XE1 or Y1. It's up to you, whatever you want to use. And this one is going to be Rn and X, let's say XRn. Now the point that is going to be explained here, how to draw delta R here. Okay, and as you see, delta R is between Rn and S. So you draw a line between Rn and S in here, straight line, and you draw another line between E and E1 and F here. Okay, between E1 and F and Rn and S. So this one is going to be like this one. Now both are going to be passing through delta R, the difference point. So the intersection between these two straight lines should represent what? Delta R. Now why we need this delta R? Because now once we know E1 here, or Y1 or XE1, I can go to the equilibrium data as we explained it in the morning here. So this one is going to be XR, and let's say this one is XE, and this is my equilibrium data, for example. So I go at XE1, let's say this is my XE1, for example. I go to the right, and I can get XR1, okay? So I come to this diagram back to the trigonal diagram, and I can draw the XR on this line, on the carrier face, and in our example was water, by the way. So this is going to be my maybe XR1, and the line connecting these 2 points will basically represent the tie line that relates E1 or XE1 with R1. Now again, I can write the same equation, material balance equation. So now this one is representing mass equation, mass balance equation, and this is going to represent equilibrium equation, equilibrium relation or equation, up to you. Now I know that if I connect this line, okay, with delta R, I try to do my best to get this right. So now XR1, I will be able to get here E2. Okay, now this is exactly the equation that I'm trying to explain here. So Rn minus 1 with E1. So now you have E1 with delta R tapta constant, doesn't change with the stages. Now if you have E1, you will be able to get R0. Now if you have E2, and this is R1, that means N is equal to 2. So that will be E2. That's why E2 with R1. So let's say now, so I have E2 my R1, E3 my R2, and so on. E4 my R3, and so on. So now that line is going to relate these two equations. So now since I have R1, I connect it to delta R and I extend the line until this point I will get E2. Now from E2 I can get the equilibrium data from this diagram again. So I can get E2, let's say this is my E2, I can get XR2. So XR2 is going to be here. Now I know XR2 is going to be related to E3 with delta R. So I connect this one and then extend this line here. And this will be my E3. And I continue with this counting down. And every tie line will represent one stage. Okay. I continue the counting until I reach somewhere here. Okay. And this is exactly what it is shown here in this diagram. So you start with this one, then you get, and the first step is to generate this intersection here, this point, and then you start y1, you get x, this is going to represent r1, because y1 and r1. Now you have r1, you can get e3, e2, sorry, and so on. Sorry. Is this clear?
So I have a question.
Go ahead.
We have this, the line from the left to the right, from F to S, right? The second line from F1 to B, how did we draw it?
From F?
From B to E1.
From B, which B? We don't have B. B is the carrier. From
R1,
I mean from B to
Rn Xn to E1 Y1.
Ah, okay. So you mean this line? How we get this line, sir? This one? You mean this line, sir?
Yeah.
Okay. Good question here. So someone is following me. Good. Yes, because now I know how to draw this one. I can locate this point, the feed, and I locate this one. But now how I know, for example, now once I know this X and B, I will be able to determine M, sir? Because M is going to be easy based on the feed and the solvent. So can we determine M or not?
We can, and we can.
You say, okay, so we'll get M. Let me do it in this way. Let me do it step by step here. So now I know F and S. So this is my F. And let's assume anywhere that solvent could be here. But now I know how to get M. So I go up here to M and I go to horizontal. And this is now my M. Okay. Now I cannot draw any random, any line that is going to pass through M point. I need to know either, I have to know this one or this one of them. So in the statement of the problem, you will be given either the location of xn or y1. One of them is going to be given to you. Okay. Once you know, let's assume you're going to use this separation process to clean the feed to become xn, let's say 5%. So now you know xn. You don't know how many stages you need, but you know the final composition or the final product or the final residual should contain not more than 5% of the solute. Okay, so now I know it is going to be at equilibrium here. So I have to know it is going to be sitting on this line. So I come to this 5% and I decide this is my Rn. Now I know Rn, it also should satisfy the endpoint. So it must pass through this point. So what I do, I go through this one and I extend it to get y1, or call it, if you want to call it, xe1. Okay, is this clear?
Yes, doctor. So either he give us the final composition.
Yes.
Or the one at the right, the first point.
Yeah, by the way, by default, most of the time you will be given the final composition. So you're usually going to have xn, and then you will be able to determine y1. Now, once you know that, because before that you cannot continue, you're going to have the degrees of freedom less than 0, which is not going to be solvable at all. Okay, is this clear?
Yes, it is. Thank you, Doctor.
Okay, so we'll see now when we start solving problems, you will understand more of this, inshallah, in the way. Now, whatever we do here in the right triangle upright, this one, you can do it with this equilateral, but I usually prefer to use this one, by the way. More easy to locate the points. Okay, so now, as you already know, minimum solvent here, it is something that we usually have to have. And as you know, in the design of any process or any equipment, we try to minimize the cost. Now, one of the any contributions to the cost is the cost of the solvent used in any treatment process. So we want to minimize the solvent quantity needed, but at the same time, we don't want to make it too much minimum. Yani, we want to know the limitation of my process. Where exactly I can start the minimum solvent? Which is the minimum? Where is exactly the minimum solvent? What is the exact minimum number of moles or kilograms of solvent needed for this specific process? Now, if you remember, I hope you remember, from the distillation, you know, the minimum represents the infinite number of stages. And you see here, the minimum comes all the time whenever you have more than one stage. Okay, so the minimum solvent, when you have counter-count stages, it is something that you want to determine based on the delta R minimum. Okay, now what is delta R minimum, or how we determine delta R minimum? Now I know this is going to be given the Rn required. Let's say, for example, you have some stages, you don't know how many stages, from 1 to, and you have solvent, let's say, with 0 composition, so pure solvent. You have this feed that contains, let's say, X feed is, let's say, 50%, just an assumption. Now, and you want to clean to obtain XRN equal to 5%. What is the minimum amount of solvent that can be used? Now, before you can determine the minimum amount of solvent, you should know the characteristic or the physical properties of the solvent to be able to generate this diagram or envelope that will be used to determine the minimum. So what I usually do, let me see here. Okay, I can't. So what I usually do, so now I know the solvent, the point of the solvent, and I know the point of the feed. So I draw the line. Okay. And now I have to draw the delta R. Okay. Now delta R should be drawn in a way that this line, you see this line, should the feed, okay, and at the same time should make a tie line. I don't know how to explain this one. So your line, this one, for a minimum condition, should be coincide. يعني يكون يحدث إن هو at the same time is a material balance line, but at the same time is a tie line, or the point here and the point here should be a tie line. Now, يعني, if you draw this line, that means now if you go to this line and you can extend this one, if you take this point and this point, these are not, this point are not at equilibrium. Okay, and they represent the actual condition. But if you draw another delta R line and you connect this point with this point, you see that these points are at equilibrium. So the conditions that are needed to determine the delta R minimum should satisfy two things. First of all, should satisfy the material balance equation plus the tie line, plus that line when we extend it and we take this point and we take this point and we compare these 2 points here in the diagram of the equilibrium, I will find this point here, and this point here. This is going to represent K point here, K, and this will represent J. So that means this line, when I connect it, is going to represent equilibrium line or equilibrium point, and at the same time, when extended, it's going to be crossing this line. And at the same time, it has to pass through the feed point. So must be tie line and must be passing through a feed point. We see this following example now shows this idea here. So you have a solution of acetic acid in water is to be extracted using isopropyl ether as the solvent. The feed is 1000 kilogram per hour of solution, contains 35% acid. So your egg feed is basically 1000 kilogram per hour. And the solution of the feed contains 35. So you have X feed here. And in most of the time, the problem is, or the composition given in the liquid-liquid extraction problems are in mass fraction. So you have acid, acetic acid, and water. So this is the carrier. Your water is the carrier. The solvent used is essentially pure isopropyl ether. So YS is equal 0. So you don't have any of the acetic acid in your solvent. The exiting raffinate stream should not contain more than this. So you have XR here. XRN is equal to 0.2. Operation is at this temperature and pressure. I will show you determine the minimum amount of solvent which can be used, and then number of theoretical stages if the solvent rate used is 60% above the minimum. So it's very similar to the requirements we used to have in the distillation. Now we want to see how we're going to determine the minimum number of minimum amount of solvent. But these are specified now. X feed, XRN is specified. I need to determine this number of stages, so I have to know the solvent rate. Now he is giving me the solvent rate in terms of the minimum solvent required, and therefore we have to determine the minimum solvent requirement. Now, as you see here, this is the water phase, and this is the isopropyl phase, which is going to be used to extract the acetic acid from water. Now, when you draw these two lines, you're going to use this, of course, diagram, very simple, straightforward. And then you're going to have this water phase, which is here 100% water. And you draw this line point by point. So you see here, let's say 1.2 ether, 0.69 and 1.2, and so on. You continue drawing all these points. You see here 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points here. Okay. Last one is going to be 16 and 46. This is the solute. This is the acetic acid here. Okay. And this is the isopropyl ether here. Okay. And this is the solvent here, solvent. Okay. So this is the first line. The second line is going to be drawn for the water phase, for the isopropyl phase, which is going to be here in this region. So again, you're going to draw this line, and we did. Now we draw this one. This is your acetic acid, which is the ACE, and you can draw point by point until you finish all these points. Now you connect these 2 points together. Is there any issue with this one? Especially when you use triangle, it's just x, y. It's like a function. You have x and y. Okay? Any question? Now we want to locate the feed points, and this is the equilibrium data. We draw acetic acid in the water phase and acetic acid in the isopropyl phase, which is the one here we have already. Here, this is. You see here, we have the acetic acid and the acetic acid here, in the solvent phase, and this is in the raffinate phase. Okay, and we do it in a rectangular coordinate here. Okay. So the acetic acid in the water phase, which is the raffinate, and this is the acetic acid, which is the solute in the isopropyl ether, which is the extract phase. And here is the diagonal line, just to show you whether you have more extension of this solute into the ether phase or in the water phase. Now we're going back to this diagram. I have the feed is given as 1000, and the XA is 0.35, which is the composition of the feed. So this is my feed point here. Second one is solvent. I know its solvent is pure, so that's why my solvent is 100%, and this is my solvent here. Okay. Now I have to draw the line between F and S, and this is the line. Okay. Now the raffinate is given as 0.29. Now you might ask yourself why we get this 0.964 and 0.016. Simply because it's given as 0.09, but you know it is at equilibrium, so it has to go through this line. So I go to 0.02, so this is 0.01, and this is my 0.02, for example. So I come here, and this is my line here. Okay, this is my point, in fact. Now I have this point Rn, S, feed, S, and Rn. Now I want to draw a tie line, then we have to draw now the delta R minimum, tie line that passes through F point. Okay, how we draw that? This is tie line. Now we will test this tie line. Is this tie line going to go when we extend it? Is it going to go through this F feed or not? Yes, you use this, of course, 19.89 here, from here, 34, this point you go there, and you find that it's around 19. So this is your tie line. Now if you extend this tie line, extend it there, you will see that tie line, if you extend it a straight line, is going to pass through your F point. And this is what exactly you are looking for. This is the line that you're going to extend to get delta R. You remember that when we said we have to, this is my feed, and I have this, I have to draw a line that is going to be passing through the feed, and it's going to be pass line. So that would represent delta R minimum. Okay, so if I do that, all what I have to do, just extend this line here with this line here. You see, this is my tie line, which is going to be representing the delta R here, the extension of that line, with the line between Rn and S. And this is going to represent delta R minimum. Now, so what we're going to do with this delta R minimum, in fact, so what we're going to use it for? Of course, we're going to use it to draw the line to get M. You remember M point? This is delta R minimum. Okay. Yes, so now when I extended this one, the crossing between this one and this one is going to get me what? E1. And if I connect it, I can get this M, and I can get what? XM here. And there is going to represent the minimum condition. Now I know XM now is equal to 0.15, I guess. So now I know this minimum will be used to, now XM is around 15.45, or 15 is enough. X feed is already given. XM is taken from the, or calculated based or located based on the minimum condition. YS is going to be 0 already, and I know the flow rate of F. I can get S minimum here. Now S minimum is representing the minimum amount of solvent needed. Now I can calculate the actual by multiplying it by 1.6. Okay, so now my actual is going to be this one. Now what are we going to use y actual for? I will get xm now, because the xm that I used before was representing the minimum condition. Now I want the actual condition, so I have to use the actual amount of solvent. I rearrange this equation again to obtain this one, and therefore xm is going to be now 11.58. Now 11.58 is representing the actual condition of the process. Any questions so far? A little bit confusing. I understand it's not easy to absorb from the first time. But by the way, if you go back and try to redo everything, use your graph paper and try to draw everything yourself, I believe it's going to be simple. And we don't have any kind of challenging questions in the exam. And we usually give you similar kind of requirements. The only changes are usually the equilibrium data, basically, or the flow rates. Okay, now once we have the XM menu, we completely set now. We start drawing our lines based on the conditions I have. I have XM and have everything. So this is the data. Again, I write it again just to remind every one of you. Okay, so this is the operating, the equilibrium line, and this is your feed, and this is your S, and this is your XR, RN. Now you have XM. What is that? Yeah. Now this is your XM new one, which is 11, I think. That's what we that calculated XM. Yeah, 11.58 here. Now I draw a line between Rn and this endpoint and extend it to get. Yeah, so I connect this one. This one will represent E1 here. Okay, and this is going to represent M. Okay. Now you have almost everything. All what you're going to start with is going to draw a tie line between this point and this point. Sorry. And you continue, and then you connect this one to this point. You get another one. You draw a tie line, and you connect it to this one, and so on. So this is again just a drawing. Yeah, so this is the first line. This is the first tie line that will represent stage number 1. You connect this one with this point. You get stage number 2. This is going to represent stage number 2. And you continue doing that until you reach the final here, which is Rn here. So now if you count it, sorry, if you count the number of stages, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Almost 10 stages are required based on the stream or flow rate of the solvent equals to, we calculated it as which was equal to 20.99 kilogram per hour. Now you can again solve the problem using, let's say, solvent of 3000. And see, if you use more than this, that means you need less number of stages, of course. Okay, but at the same time, it's not something that you decide based on just the number of stages, because the decision made is really based on so many other factors, and usually made based on some kind of optimization for the whole process, not only the liquid extraction section only. Okay, any questions so far? Inshallah, see you on Wednesday, because the I will end the session now. We'll see you, inshallah, on Wednesday at 8 o'clock. Hopefully, see some few guys. Wednesday we will have the quiz at 6 p.m. Okay, so please try to spread this message. The quiz will be at 6 p.m. in the evening, because some of the students are really willing to participate in the celebration of the National Day, so we don't want to prevent this from happening. But the quiz is around, it's going to be around half an hour. I will post also the last assignment on Wednesday, and it's going to be about HISIS, so you will be asked to do something, some separation or design of separation, maybe Flash or distillation column using HISIS software. Hopefully everyone has access to HISIS. If you don't have access to HISIS or you don't have the license, I believe you're allowed to come to the university to conduct your homework. Yeah. So that's it for me. And if you have no more questions, I wish you all the best, inshallah, in your National Day, and see you on Wednesday. Okay?
Doctor, can you upload the slides as well?
Yeah, of course, I will do. Thank you for reminding me, Lena. You keep forgetting you. So, inshallah, I will upload it right now. And if I don't, please remind me, okay? And again, there's one last announcement regarding the evaluation, course evaluation. Please, you are encouraged to go there and just have your say. I want to see your feedback, and if there is anything that we can do to improve the way how we teach the course, or if there is any comments you wanted to you want people to listen to you without knowing your name, it's good. This is your chance, okay? But try to be realistic a little bit. Some of the comments we might have control over. Sometimes we don't have control over the suggestions, so we're trying to do our best. But without your feedback, we usually don't have to improve anything, since we don't have anything, any characteristics. Okay. Thank you very much. Inshallah, see you on Wednesday at 8 o'clock in the morning. Hopefully, everyone is going to be awake. Thank you. Assalamu alaikum.